today with the questions in your notes. Remember that the standard formula for a quadratic, and it has to be a degree 2, which means its highest exponent is 2. All right, there's your first blank. The equation for that polynomial is y equals ax squared plus bx plus c. That is your actual standard form for a quadratic. Again, it's different for a line. You know another equation for that. Next thing we wanted you to do was explain what you need to know about a quadratic if it's in standard form. In other words, what pieces will you look for in order to put them on the graph? And one piece is, for quadratics, you should be looking for x-intercepts. And the x-intercepts help you find the axis of symmetry. And then the axis of symmetry will help you find the vertex. And another thing you can look for is the y-intercept along with its corresponding point. And remember, corresponding just means a symmetric point. You flip it across the x-axis. So these 4 things basically. Your next question asks you to explain how you would find those. So we're going to leave that on the same screen and do that. To find x-intercepts, you simply factor. That's why in standard form, a lot of times you want to factor. And then once you get your factors, you set equal to 0 and solve. That creates your x-intercepts for you. The axis of symmetry then is just that midpoint of the x-intercepts. That's why how we found that. The vertex uses that axis of symmetry as its x-coordinate, and then to find the y-coordinate, you plug the x into your formula, your function. Okay. And finally, for the y-intercept, if you are in standard form, it's simply that c value. It's 0c. But if you're in any form, you simply let x equal 0 and solve. I don't really have to here though, because 0 plus 0 gives you just the c value. Alright, so that's standard form. If we're in vertex form, remember, looks like this. That's what we were hoping you would put on the blank. And with vertex form, it's simple to find your vertex. It's just the opposite of whatever's with the x. Right? To answer the question, what would you need? You would need the vertex and you would need your transformations. Right? And the vertex being just the opposite, so that h, and then the y value is just the k value outside, that up or down. So it's just your left-right movement and then your up-down movement. That's the way you want to think about it. And how you would find those things? Well, we just talked about the vertex. And then once you know your transformations, you simply take the vertex and you move it all the rest of those transformations. You reflect, you stretch, you compress. All right? So we're going to look at example 1. And example 1 has something different that we haven't seen in a little bit. It has this x, the value inside with the x. We are going to factor the 2 away, but it stays inside of that squared piece. So we'll have 2 parentheses, and that'll leave us x minus 3, but it's that whole quantity still that's squared, keeping your minus 2 on the outside. Looking at this then, we're going to name our transformations, which would be, remember it's not 2 but a half, so it's a horizontal compression of a half. It will go right 3, and it will go down 2. We're simply going to do all of those things. As we go right 3 and down 2, that creates your vertex. This one doesn't reflect, so it still will be a minimum. We know our vertex, so our axis of symmetry is just x equals the x coordinate. We can even y equals x squared, which tells us if we go right 1, we'll go up 1 squared. If we go right 2, we should go up 2 squared, or 4. Right 3, up 9, and so forth. So to do that, I'm now going to have to compress that though. So instead of going right 1, I'll only go half of that, or right a half, but I'll still go up 1 unit. And I can find its corresponding or symmetric point on the other side, which would be at 2.5, -1. Then I can do the same thing. I can go right half of my 2 values, so I'll only go 1, but now I can go up 4. 1, 2, 3, 4. Left 1, up 4. That's going to change your picture a little bit. I hope that you see it makes it smush in on the sides, or it makes it sort of tall and skinny. Also, think about what else that looks like. A horizontal compression should make you think of another type of transformation. Okay, take a look please at number 5. Go ahead and flip to 5. On 5, we're doing the same thing, but now we have a fraction. So we'll get f of x. We'll leave that negative in the front. Inside of our parentheses, we are pulling the 1/3 away, so we have another set of parentheses. That will be x minus 1/3 times what gives you 2? Well, that'll be a 6, because 1/3 times 6 would be 6/3, which is 2. We'll close this parentheses and close our larger parentheses to put the square outside. Everything, including the 1/3, is still squared, so it's in our function. We keep the +3 outside. To name our transformations now, we know that the 1/3 is actually going to become a 3, and it's with the x, so it'll be a horizontal stretch of 3. It will go right 6, not 2, but 6. It does have a reflection over the x, and it will go up 3. So as I go graph that, we can graph or name our pieces and parts first, either way. If we do the parts here, that would go right 6 and up 3 for our vertex. This one reflects, so it will have a maximum because of the reflection. Axis of symmetry is going to be that x equals 6. Domain, all real or -infinity to +infinity. And because it's turned down, our range is a -infinity up to the vertex y value of 3. Bracket, because there's always going to be a point there, parentheses on infinity. So when we go right 6 up 3, we'll be up here. We know we're going to turn down, and again, if you think about that 1, 1, 2, 4, the horizontal piece, the x part, is what's going to be stretching. So instead of 1, I'm going to go 3 to the right, but I only go down 1. I'll go 3 to the right, 1, 2, 3, but only down 1. And I can do that again. I would go not 2, but 6 to the right and down 4. And 6 to the left and down 4. That's going to fall off of your graph a little bit. When you graph that, what do you notice about the shape? Hopefully what you notice is it's making it wider, right? So a horizontal stretch pulls it to the sides. It should also remind you of another transformation. Right? Last one that we're going to look at is number 9. If you'll flip there, please, with me. And number 9, we're not even going to bother with the graph. We just want to we want to go through and complete the square. You did some of those in class today, but I want you practicing. I want to walk through it one more time with you. As you look at this, the 1/2 now is factoring away. This one is different than this because the 1/3 was in the parentheses being squared. Here, whoops, sorry, on number 9, only the x is being squared. So when I pull that 1/2 away, it is not being still inside of a parenthesis squared or anything. So again, we're factoring 1/2 out of the 2x terms only. We don't touch that 10. So 1/2 times x squared gives me the 1/2 x squared. And 1/2 times a negative 10x will give me negative 5x. We're always going to put our little blank there so that we can complete the square. And go ahead and keep your plus 10 outside. And you've got to balance it. Since we're adding something here, we're going to subtract the same something. Our blank is being multiplied times 1/2, so this blank also has to multiply times 1/2. Right? Shortcut of finding this is take your x terms coefficient, the b value, 10, and take half of that. Half of 10 is 5, and you're going to square that. So that will be 5 squared, 25, 25. When you factor now, you're going to get x minus 5, quantity squared. Out here you've got 10 minus half of 25 is 12.5. So that winds up being a negative 2.5 or a negative 5/2. And this is your vertex form. Thank you.